everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, intersection of two arrays. We're given two integer arrays, nums1 and nums2, and we want to find the intersection of them. They don't really define what exactly that is in this problem, but basically it's elements that are common to both of the input lists. Now it's possible in this case, for example, we have duplicates, like we have two 2's here and two 2's here. But for the intersection, for the output, we do not consider duplicates. So the result must be unique. So this is a relatively straightforward problem. The hint is that since we don't want duplicates, the easiest thing we could do is put everything in the first set or the first list into a hash set and do the same thing with elements in the second list, put them into a separate hash set, and then at the end we can check elements that are common to both of the hash sets and then include them in the output. So while that's definitely possible, we can actually also solve this problem with just a single hash set. Let me show you how we're going to do that. So suppose these are our two input arrays. Let's say we have a hash map and we're going to map every single element to a Boolean. So when we go through the first array, we have 4, we're going to map 4 to a Boolean. We're going to do false, so I'm just going to put the letter F here. And actually, I think I just realized we don't even need a hash map. We can probably just use a hash set, so I'm going to do that to make this even more simple. So now we don't have to worry about mapping these to anything, but we'll have 4, we'll have 9, and then we'll have 5. So we'll add every element in the first array to a hash set. Next, we want to go through the elements in the second array. Now we want to find common elements. Any element in this array that also shows up in the hash set. For example, first element is 9. This does show up in the hash set. That means it's common to both arrays. That means we should add it to the output. Next, we get to 4. Same thing. It's common to both arrays. Let's add that to the output. Now we get 9. So this is the part where we might end up with duplicates, so we want to handle this pretty carefully. We don't want the same element to show up in the output twice, but how can we detect that? How can we know that we've already seen this before? Well, the first time we saw 9, we should remove it from the hash set. Same thing with 4. When we see 4, we see it's already in the hash set. That's great. We add it to the output, and at that point, we should remove it from the hash set. When we get to the second 9, we won't have any 9s in here, so we'll skip this one. Then we'll get to 8. 8 doesn't show up here at all. And then we'll get to 4. It has been removed, so the output in this case is just going to be 9, 4. And that is the correct output for this example problem. So this is probably the most straightforward and efficient way to solve this problem. It's going to be linear time and linear space for the hash set. I guess it's worth mentioning that there probably is a sorting approach solution for this. In that case, we would not need extra memory, well, depending on the sorting implementation, but that would be one way to optimize the space, but it's going to cost us when it comes to time. It's going to be n log n in terms of time. Okay, now let's code this up. So the first thing I'm going to do is just get that hash set that I talked about. We could manually instantiate it and then create it ourselves. It's pretty easy to do that for n in nums, and then we could say scene.add n. So that would be going through nums1, but it's even easier if you're allowed to do this in an interview, which usually you will be allowed to because this is pretty simple. We can just pass nums1 into that and then get a hash set from those elements. And next, we can build our output result, which is what we're ultimately going to return. So I like to write that out at the beginning. And then to actually build it, let's go through every number in the second array, n in nums2. And if n is in the hash set, then it's common to both arrays, and therefore we should add it to the output, just like this. But let's not forget, we should also remove it from the hash set because we don't want to end up adding it multiple times. So here, let's say scene.remove n. And let's go ahead and run this code because this is actually it. And as you can see on the left, it's pretty efficient. If you're preparing for coding interviews, check out neatcode.io. Thanks for watching, and I'll see you soon. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve top k frequent elements. I really like this problem because it's pretty clever, and once you figure it out, the code is really easy to write. So we're given an input array nums and an integer k, and we want to return the k most frequent elements that appear in the array. For example, for each value, right, we're in this case, right, basically if every single value in here was distinct and we wanted the top k distinct values, we'd get a time complexity of n log n, right? But we don't necessarily need to sort the entire thing because we only want the top k frequent elements. So in another solution, we could actually use a max heap. So we would still do this whole operation where we count the number of occurrences of each value, and then we'd add each pair to our max heap. And the key of this max heap would, of course, be the number of occurrences, right? So the count, right? And then we'd pop from our heap exactly k times. So why is this more efficient? Well, we know popping from the heap. Well, first of all, when we initialize our heap, we're going to add this entire set, and there's a function called heapify, I think, that can do that in actually linear time, so big O of n times, so that's the good thing. And of course, we know we're only going to be popping from the heap k times. Each pop is going to take log n, and we're going to be doing that k times, right? So that's going to be k times log n. right? So that's a little bit better than n log n, at least as long as k is less than n, right? But it turns out that there's actually an even better solution. There's actually a solution that can be done in O of n time, linear time. So big O of n time and big O of n memory. But we are still going to be using this exact technique where for each value, like 1, we count the number of occurrences like 3. So this problem can actually be solved in linear time if you use the algorithm called bucket sort. So when you first think of bucket sort, this is probably what you're going to think of. The way bucket sort is usually taught is that for each value, for example, 1, we're going to take an input array, right? This is our input array. This row is the indices, the index of the array, and this is actually going to be the value. So for example, for 1, we're going to go to the index 1, and in the value, we're going to put, okay, 1 occurs exactly once. Now we're going to see a second one, we're going to say 1 occurs twice, right? Basically, we're going to go through the input array, count how many times each value occurs, and then in our input array, put that count for that index, right? Map the value to the index and then put the count of that value. So 1 occurs 3 times, 2 occurs twice, 100 in this case occurs once. Now this algorithm would be linear time if our input values, right, were bounded. For example, if we knew for a fact that every value was between 1 and 10, then we would know that the size of our input array is also going to be 10, right? But in this case, the values are unbounded, right? Like this could have been 1,000,000, and then the size of our input array would have been 1,000,000, even though the total input array size is only 6, right? We have 6 elements, but then that array where we actually store the bucket sort values is going to be unbounded, right? And also, we want the top k elements. This still isn't very clear of where exactly the top k elements are actually going to be. So in this case, this type of bucket sort doesn't work, but there's another way we can do it. So in this case, you can see for our array where we're going to be doing the bucket sort, the index, I was using each value in the input array. For example, 1 was being mapped to index 1, right? And there we were storing the count. There's actually another tricky way that you can do it that will lead us to a linear time solution. So if we're pretty clever, this is what we're going to do. For the index, we're actually going to be mapping the counts of each value. And in the values, we're actually going to have a list of which values have exactly this particular count. For example, problem IPO. We're given 2 arrays. One array is the profits array, and another array is the capital array. Suppose something like this, where we have 1, 2, 3 for our profit values, and 0, 1, 1 for capital. We're also given an initial capital called W, let's say it's 0 in this case, and we're also given an integer k, in this case 2, so you can see there's quite a lot of variables in this problem. Our goal is to maximize the amount of money, aka capital, that we have at the end. Initially we have 0. So what we would like to do is take some of the profits. So maybe we take 2 and we take 3. We can only take up to k of these values. And when we take them, we mean add them to our This is not like the cost it takes us. This is the capital. So as long as our capital is greater than or equal to this, we are allowed to take. This is initially our, aka we should maybe take all of these and throw them in a min heap, not based on the profit though, but based. Hey everyone, welcome back. I hope you're having a good holiday season, but don't forget your daily dose of neat code. So today let's solve a reorganized string. This is a pretty solid and even somewhat unique problem. So we're given a string S, and we want to rearrange the characters of S so that any 2 adjacent characters are not the same. So that's a pretty simple explanation. If only the solution were as simple. And by the way, if it's not actually possible to do that, we have to return an empty string. So that's something to keep in mind. So let's look at these examples. So if we had 2 A's and 1 B, That's pretty simple. We'd put an A first, then a B, and then an A. In this case, no two adjacent characters. So if we want to be able to hash map, but is a hash map going to be enough for us? So how would we rearrange these? Well, of course, we'd want to start with the most frequent one, so that's pretty easy to do. We'd find that A is the most frequent. There's 3 of them, so we start with A. Okay, what goes next? Well, does it really matter if we put B or C next? So we can put a B or C's, and then we're left, just one A, so then we just put the A at the end. So that worked. Is that going to be an approach? Because that's one of the first ideas I had when looking at this problem. Let's just start with the most frequent character and then put another A, right? This does work. And this is the solution. And by the way, of course, A, C, A, B, A also works. And thankfully, they say that we can return any valid string. So either of these solutions would be fine. But how come our algorithm couldn't figure this out? Because we're kind of cycling through each of these. Is there a bit? Because we know if we try taking the most frequent character again, which is an A, we're going to get 2 consecutive A's. That's not exactly what we want. But we can basically put this value on hold for a while. We just used an A, so we're going to say, okay, find the most, make this clean, A through Z. So the actual algorithm would be 26 of n, and I don't know if this gets accepted on LeetCode or not, because there's actually a slightly more efficient, but what we want to actually add to the min heap is the count, of course, because that's how we're sorting this, right, based on the count. So what we're going to do, this is some Python syntax. So don't let it confuse you too much, but basically we're going to iterate through each character, each count in our count hash map. We're going to iterate through the items of it just to be able to have both of the values just from a loop. And then doing this, we're going to build a list right now. I think this is called list comprehension in Python, but you don't have to do this syntax if you don't want to. I just think it's a little bit cleaner. And basically for each character and the count of that character, we're going to take that count, make it negative, and that's going to be the first value, and the second value in this pair is going to be the character itself. And basically what this is doing, it's adding a pair of each character with its negative count to a list. And the reason we're putting the count first is that basically on average it'll run in big O of n time. And you can Google that if you don't believe me. And now we're actually going to start basically building our result. We're going to be getting the most frequent. That makes sense to me, so that's what I'm going to do. And actually, we don't want to set it to previous if the count reaches. So you could say not equal to 0, or you could even say if it's to null. And then maybe if the next. So our max heap is actually empty. So if previous is not solution. Okay, so that's pretty much why I put an and condition. We don't need both of these to be non-null because, of course, previous is going to start to be null. Basically,
Now let's build our binary search tree constructor. The first thing we'll need to do is build a node. And remember, this node is going to look something like this. So the constructor is going to look like this. Value, left, and right. And once we have this, we can start building our binary search tree. We'll start the constructor out like this. And I'm just going to focus in just on the constructor like this. We pass it a value, and we use that to create a node like that. So to explain what we're going to do in the next line of code here, I'm going to make this part of a tree like this. Each node needs to have something pointing to it. And every node in this tree has something pointing to it except that first node. So we saw this concept with linked lists. If you're going to have a linked list, you have to have something pointing to the first node, because that's the only way you have a way of getting to that node. So in a tree, we have something similar. We don't call it head, we call it root. So we have to create this root variable. So we're going to say self.root equals new node. And we're not not going to keep track of the length in a tree. So this is a working binary search tree constructor. But I want to teach a different concept here. So I'm going to remove the code here. And we're making the assumption when we build this binary search tree that we're going to create this with the first node at the time that we build the tree. And you don't have to do it that way. We've done it that way on all of the data structures so far. But you could just create this where root is equal to none. You create an empty tree, and when you add the first item, you add it with the insert method. You don't add it at the time that you create the tree or the linked list or whatever you're building. So what I'm going to do is I'm going to bring this code back and change it where it creates an empty tree at the time that we run the constructor. So I'll go through this line by line. So in the first line, we passed this a value. The only reason we did that was to create that first node. So now we can remove that. The second line, all this does is create a node, so we can remove that. So this last line, self.root equals new node, we're going to change that to be equal to none. Now that becomes our entire constructor for initializing a binary search tree. Now let's bring back where it said class binary search tree, and let's go look at this in VS Code. So there is our class for our node there, and that has value left and right, and this is our class for our binary search tree. And then for our binary search tree, that is the entire constructor there. Then we're going to create a new binary search tree called myTree. And then down here, we'll just print out myTree.root. And it should return none, because up here we said that self dot root was going to be equal to none. Okay, so I'm going constructor. In this video, we're going to walk through the steps to create the insert method. Then in the next video, we'll take those steps and walk through them and actually create the code. So I'm going to bring up our binary search tree like this, and we're going to insert this node. And obviously that's going to fit right there. But let's walk through the steps that you would have. In this video, we're going to walk through the steps to create the insert method. Then in the next video, we'll take those steps and walk through them and actually create the code. So I'm going to bring up our binary search tree like this, and we're going to insert this node. And obviously that's going to fit right there. But let's walk through the steps that you would have to go through to be able to write the code to figure out that it does go there. So the first step would be to create a new node. So what I'm trying to do in this video is go through the steps that you would go through if you took out a piece of paper and said, okay, I'm going to figure out all of the steps to insert a node into a binary search tree. So the left is essentially our piece of paper that we're taking notes on. So in order to have more room for that, I'm going to move our tree over like this. And now the next step. We need to compare that new node with a value of 27 to this node here. And if the node we're adding is less than, we're going to go left. And if it's greater than, we're going to go right. So let's add this to our notes over here. If it's less than, we're going to go left, else it's greater than, and we're going to go right. And obviously in this case, we're going to go to the left. And when we do, there are two possibilities. Either there is a node in that spot to the left, like we have here, or there isn't. And if there isn't, we can just insert it right there. So if to the left of the 47 is equal to none, we'll insert it. But if it isn't, then we need to come down here and do the whole process again. So we could say if the direction we're going is none, then we'll insert the new node, else we'll move to the next node. So now we're going to compare our new node to this node, the 21 node. So we're going to do this again. If it's less than, we go left, else it's greater than, and we go right. So in this case, that's going to be to the right. And when we go to the right, we have to determine, is that spot empty? Is 21 right equal to none? If it is, we're going to insert it, and in this case, it is. So the thing that should jump out at you is that we did these two lines of code for this node, and then we did it for this node. So that is an indication that these two lines of code should be inside of a loop. And because we don't know how many times we're going to be iterating through the tree, this cannot be a for loop. It has to be a while loop. Now, as we were iterating through this tree, we had this arrow that was pointing at the node that we would compare the new node to. So we need to name this arrow. We're going to call this temp, and then it will move through the tree, and we will compare new node to temp. So I'll bring this up here. We need to have this start at the top of the tree. So we'll set it equal to root. And we need to declare this variable before we ever get into that while loop. So we'll need to put this above that. So these steps right here cover most of our situations. But we do have a couple of edge cases. The first one being if we have an empty tree. If this happens, we'll just set root equal to the new node like this. And in this situation, we don't need to go through the while loop. We don't even need the temp variable. So we can put this above the temp variable like this. If root equals none, then we'll set root equal to the new node. So let's bring our tree back like this. And we do have one other edge case. And to show this, I'm going to replace our 27 node with a 76. So if we're going to insert this, we'll start at the 47 and then we go right, and now we have a problem. You can't have this be equal to a node that we already have in the tree. All of our code that we've written is less than go left and greater than go right. There is nothing in there for equal to. You cannot have duplicates. The new node that we're inserting needs to be compared to each node as we're moving through the tree. So this has to go inside of our while loop. If the new node is ever equal to temp, in other words, the next node that we're comparing it to, at any time, we're going to return false. And that is the last step that we need to write down. Right here in the next now, those. Okay, so now let's code our insert method. And as I mentioned at the end of the last video, we're going to start right where we left off with the other video with all of these notes. I'm just going to bring these down. here to the bottom, and we'll start coding this. So we're going to say insert, we're going to pass it a value, and then we'll come down here to the nodes. The first thing is to create a node. So we'll do that like that. That creates our node, and we can remove that from our list. The next item on the list is if the root is equal to none, then we're going to set root equal to new node. That is this situation here where root is equal to none. We have an empty tree, and we're going to set root equal to the new node. We'll do that like this. If root is none, root is equal to the new node. But there is one other line of code that we need here. We need a return statement. Because if we're going to insert this directly into our tree at the root, we don't want to continue running code in this method. So now we can remove that. Then we're going to say temp equals self.root. That's actually the way we would write the code to declare that variable. So we can just move that up. So that brings us to our while loop. So our while loop is going to be while true. And normally you run a while loop until this condition is false, and obviously true is always going to be true. But the way we're going to break out of the while loop is by hitting a return statement at some point within the loop. So remove that. Then we'll say if new node equals temp, return false. And that is this situation where the new node is equal to another node in the tree. And if this happens at any point, we need to return false. So we'll do that like this. If new node dot value, and it's important that you not just say if new node equals temp, you have to say new node dot value and temp dot value because we're comparing the values. If they are ever equal while we're running through the while loop, we're going to return false. So now we can remove this. Now we're going to say if it's less than, we're going to go left, else the number is greater than, and we're going to go right. So we're going to start with left, and we'll say if new node dot value is less than temp dot value. And since we're running out of space here, I'm going to move this if statement up to the top of the screen. But I want you to notice that this is inside of our while loop. So everything we're going to do to code out the rest of this method is going to be contained in that while loop. So we're going to move this up like this. And the second if statement in the notes down here is actually nested inside of the other if statement. And we'll see that in a second, but for now I'm going to remove the notes, and it's going to be easier to finish explaining this by bringing up a diagram. So we're going to insert this node here, and remember temp is going to be pointing at the root here. So this if statement at the top, we're saying if new node dot value is less than temp dot value, and in this case it is. So that means we know we're going to go left, but there are two ways we can go left. Either that spot is open like this, in which case we're going to place that node. Otherwise, there will be items here, and then we'll need to compare the 18 to the next item in the tree. So let's assume that this spot is open first, and we'll say if temp.left is none, which means that spot is open, we're going to set temp.left to be equal to the new node. Now that we've placed that, there's one more step that we need to do here. And we need a return statement. So we'll return true. So that's what we do if that spot is open. If the spot is not open like this, we need to move the temp variable down to point at that 21. So we'll say temp equals temp dot left, and it moves temp down. And remember, this is all inside of this while loop, so now we're going to run through all of this again. So obviously we're going to go left because the 18 is less than the 21. So then we come to this line. If temp.left is none, and in this case it is none, then we're going to set temp.left equal to the new node like that. And then, of course, we'll return true, and we're done placing that node. Now let's look at inserting something on the right. I'm going to bring our temp variable back up here. I'm going to move this to the left since we're going to be inserting on the right. We'll need a little bit more room. So for this, we're going to say else, and I'm going to remove that 82 node on the lower right-hand corner of our tree there. That'll be the one we're going to insert. And just like on the other side, we can have a situation where we have a node to the right of the 47, or that spot can be empty. If that spot is empty, we'll say if temp.right is none, and in this case temp.right is none, then temp.right equals new node. That is temp.right equals new node. And then we need to return true. The other option is that there is an item there, and then we'll say temp equals temp.right. That is temp.right. That moves temp down. And remember, this is in a while loop, so that causes us to go through all of this again. So then we'll say if temp.right is none, and in this case it is none, then we'll place that temp.right equals new node. That is temp.right equals new node. And that is everything we need to do to be able to insert that node. So now let's look at this code in with the rest of the code that was in the while loop. That is our full while loop there. So to walk through this, this is for the situation when we try to place a node that is a value that is already in the tree, like this, an identical value. Then if it's less than, we go left. If it's greater than, we go right. And we'll look at this in a moment in VS Code. So let's flip over and so now we're going to write our contains method. So for contains, we're just going to see if a tree contains a particular value. So if we were looking for the number 27 that is in the tree, we would return true. If we were looking for the number 17 that is not in the tree, we would return false. So just like we did for insert, I'm going to walk through all of the steps for the contains method, and then we will go through the code. So the first thing we've done in all of our data structures to this point is to code for a situation where that data structure is empty. So we'll say if root equals none, we'll return false. And we'll talk more about this scenario at the end of the video. But let's bring our tree back like this. So the next step is we'll need a variable that we'll use to traverse through the tree. We'll call that temp. So let's say we're looking for the number 27. It's less than 47, so we go left. It's greater than 21, so we go right. And now it is equal to. That means we've found the value. So let's bring this up to the top here and actually create that variable. We'll say temp equals self.root. So now let's look at what happens if we're looking for a number that is not in the tree, like the number 17. We're going to go to the left. 17 is less than 21, left again. It is less than 18, we go left again. If we ever get to a point where temp is equal to none, that means the number we're looking for is not in the tree. And it also means we should stop iterating through the tree. So our while loop is going to say while temp is not none, we'll continue doing this while loop. If we ever hit none, that will break us out of the while loop. Inside the while loop, we have 3 scenarios. Either the number that we're looking for is less than temp, in which case we're going to go left, or it's greater than, we'll say else if it's greater than, we'll go right, and then our third scenario is that it is equal to. So whenever the value that we're looking for is equal to temp, we'll return true because that means that value is in the tree. If we ever hit none, that means that number is not in the tree. It'll break us out of our while loop, and we will return false. Okay, so those are all of our steps for the contains method. let's move those steps down to the bottom here and write the code. So we'll say contains, we'll pass it a value, the value that we're looking for. And now let's start working through our list. If root is equal to none, we're going to return false. So that is this situation where we have an empty tree. So we're going to say, if root is none, we return false. And we'll remove that from the list. Next, we'll create our variable temp equals self.root. And that's exactly the way we would write the code. So we can just move that up. Then we'll create our while loop. And this is actually the way we would write the code. While temp is not none, we'll just move that up. Then inside of that while loop, if it's less than, we go left. We'll write that code like this. So let's walk through this. We're saying if value, the value that we're looking for, is less than temp.value, in this case that's 47. Let's say we're looking for 27. That would be less than. We would say temp equals temp.left, and that moves that down. So let's remove this tree, and we can remove that item from our list. Then we'll say else if it is greater, we'll go right, like this. This is saying if the value we're looking for, say that's the number 82, if it is greater than temp.value, in this case 47, we're going to say temp equals temp.right, and that moves temp down. So let's remove that, and then we can remove that item from our list. And then finally, we're going to say else it must be equal, and we're going to return true. And then we'll just do this because that is the only option that we have left if that item is in the tree. So we'll remove that. Then there is also the possibility that that item is not in the tree. That'll break us out of the while loop, and then we will return false. Now let's zoom in on this while loop and just walk through a couple of scenarios how this code would run. I'm going to bring a tree up here, and for this first one, we're going to look for the number 27. So we're going to say while temp is not none, which is to say while it's still pointing to a node, this will run. If value is less than temp.value, and it is, 27 is less than, we're going to say temp equals temp.left and move this down. Then we'll run the while loop again. If it's greater than, we're going to move right, and it is greater than. And then we'll run the while loop again, and this time, that is the value we're looking for, and we're going to return true. Let's bring this up here and look for a scenario where we don't have that item in the tree. We'll look for the number 17. So we'll say while temp is not none, we're going to go left. Runs the while loop again, and we're going to go left again. We run the while loop again, and now it's less than again, and temp.left equals none. Now when we run the while loop, temp is equal to none. It breaks us out of the while loop. And we return false. So let's drop this tree out of here, and we'll bring in the rest of our code. Very common to see code that has the equivalent of these two lines in there. And you can see why. Whoever created that code went through the steps on a piece of paper. They wrote this out. We're going to set temp equal to self.root. That's just going to make temp equal to why. Whoever created that code went through the steps on a piece of paper. They wrote this out. They put this in their code, and it works. So I'm going to remove this, and we'll walk through a situation where we have an empty tree. We're going to set temp equal to self.root. That's just going to make temp equal to none. We move down to our while loop, which says, while temp is not none, while temp is none. So we're going to skip that, and we're going to return false. So that is the final version of our code for contains. So this is what we're going to look at in a moment in VS Code. Contains method